Dear students, today we'll see what do we mean by active high pass filter, which comes in the analog electronic circuits. So the topic will be active high pass filter. Now here if you see basic definition, what is a high pass filter? The definition of high pass filter is a filter which passes only those signals whose frequencies are higher than cutoff frequencies, thereby attenuating signals of lower frequencies. The value of a cutoff frequency depends on the design of the filter. Okay, so here what we are saying is, say if you draw a graph of the output, say this x-axis is frequency and y-axis is the gain. Okay, then you will have a cutoff frequency at some stage. This will be your cutoff frequency. Now, any signal whose frequencies are below the cutoff will be stopped. So this will be your stop band. And any signal whose frequencies are above the cutoff will be passed. So this will be your pass band. So this can be your ideal sharp cutoff frequency, or practical if you see, you will get it something like this, and you will get a pass band over here. Okay. Now, a cutoff frequency is very important because that is the reference above which all the signals can be passed, below which all the signals will be stopped. So it is called as high pass filter. Same definition, if you go in the other way, you can see that a high pass filter will allow the frequencies which are higher than the cutoff frequency and attenuate the frequencies lower than the cutoff frequency. Okay. Now, basically, a high pass filter can be achieved by connecting a capacitor in series and a resistor in parallel. So, as shown here, so if this is your input, this is where you are applying your input signal. Okay, so this input signal will go from 0 to some hertz. Okay, some hertz, and in between that you will have your cutoff frequency. Okay, so 0 to cutoff frequency will be stopped, and cutoff frequency to the maximum frequency will be passed. That is the case. Now that happens because you're connecting C in series. C in series means C will allow AC, it will allow frequency higher, and it will block DC. That means the impedance given by the C, the reactance, the opposition to the flow of current, reactance provided by C is given as XC is equal to 1 by 2 pi FC. Now here frequency is inversely proportional to the reactance of C. That means if frequency is high, reactance will be less. If the frequency is low, reactance will be more. That means from 0 to the cutoff frequency, these are lower frequency then, and from after cutoff till the maximum, this will come at the higher frequency. So this will be passed and this will be blocked. As the frequency is decreasing, it will be blocked, and as the frequency is increasing, it will be passed by the capacitor. Similarly, the resistance in parallel will see that the lower frequencies go to the ground. Okay, that means whatever pass here is high frequencies only. High frequencies only. Now this is a passive high pass filter. Now this is what you will get the output with by just connecting capacitor in series with the source and a resistor in parallel with the source. Now output of this will not have much gain. So the gain will be not very much. And if you want a bigger gain, a greater gain, then you have to go with some active device like a transistor or op-amp. So along with this C and R combination, if you use a transistor or op-amp, then this passive filter becomes active filter. And if you use one set of C and R, it will be called as first order. If you use two sets, it will be called as second order. Okay. So it is an active filter if you use a active component along with this passive C and R. So here, if you see the definition of active high pass filter, an active high pass filter can be created by combining a passive RC filter, as we have seen earlier, with an operational amplifier to produce a high pass filter with amplification. That means the output will have certain gain depending upon the amplifier configuration of the op amp. Okay. Then here we see the circuit of the passive R and C are connected along with op amp. Okay. So here you can see the passive C is connected in series with the input and R is connected in parallel with the input. So this is going to pass your high frequencies. So high frequencies are passed and low frequencies will go to the ground. Okay. Now this high frequency which is passed is given to the non-inverting terminal of op amp, and in the inverting side you see R2 and R1 which will decide the gain of the filter, and depending upon that gain amplification will happen and the output what you get will be a amplified version. This is a amplified version, or this was actually your input. Now all the signals which are your above cutoff frequency will be passed, and all the signals which are below cutoff frequency will be blocked, and that cutoff frequency will be decided by the value of a capacitor and resistor, that is C1 and R3 in this figure. So this series capacitor and the parallel resistor will decide the value of the cutoff frequency. That is very important. What value you take of C1 and R3. So those values will give you the cutoff frequency. Now here, explanation for the circuit. This first order high pass filter consists simply of a passive filter followed by a non-inverting amplifier. The frequency response of the circuit is same as that of the passive filter, except that the amplitude of the signal is increased by the gain of the amplifier. The non-inverting amplifier using op amp, whatever you are having, that will increase the amplitude of the output. But the frequency response remains same because it is controlled with the C and R combination of high pass filtering. That means here, this section is going to do your high pass filtering where you have C and R. So this section is going to do your high pass filtering. And this section of op amp is going to do the amplification process. Okay. So then if you go to see the formula for a cutoff frequency, then for a cutoff frequency of active high pass filter is given as Fc, that is cutoff frequency is equal to 1 by 2 pi R into C, that is the value of resistance which is in parallel with the input and a capacitance which is in series with the input. So those two values will decide what should be the cutoff frequency. The gain of the non-inverting amplifier, as we know because of op amp configuration, AV will be equal to plus R2 upon R1, 1 plus R2 upon R1, that is 1 plus feedback resistor upon input resistor. That will be the gain, that is how many times the output is with respect to the input. If you see the theoretical graph, that is frequency response, then you can see that you are having a cutoff frequency which is named here as FH. So here you can see this can be your cutoff frequency FH. Now above cutoff frequency everything is passed, and below cutoff frequency everything is stopped. Okay, so this is your ideal high pass filter frequency response, where x-axis you're taking as frequency and y-axis you're taking as voltage gain. Similarly, if you see the practical response, then you will not get a sharp response. You can see that there is a sudden increase here once you reach to the cutoff frequency. When once you are nearer to the cutoff frequency, then you see that the gain of the output goes on increasing here, goes on increasing, increasing. This increase will be at the rate of plus 20 decibels per decade of frequency, plus 20 decibels per decade. Okay. Now this will go, and then at one stage it will remain constant. It will remain constant. Okay. So this is your maximum gain. This is your maximum gain. Okay. Now to plot the cutoff frequency, you have to come to 0.707 of maximum gain. That is 70.7% of the maximum gain, which in decibels will be minus 3 decibels. If you come down, then you will have this line. Okay, and this line will cut here, and this line, when you project it on the frequency, will give you the cutoff frequency of high pass filter. Now all the signals above this frequency will come under pass band, and all the signals below the cutoff frequency, which will be stopped, so it is called as stop band. Okay, so here again you can see the same type of graph shown in a hot color picture. That is frequency response. The slope, you can see it is plus 20 decibels per decade, and you can also refer a bandwidth in the pass band. Okay, and stop band and pass band also is shown in this figure. Lastly, if you go to see the applications of high pass filter, these filters are used in speakers for amplification. High pass filter is used to remove unwanted sounds near to the lower end of the audible range, to prevent the amplification of DC current that could harm the amplifier. High pass filters are used for AC coupling. High pass filter is used in image processing, where high pass filters are used in image processing for sharpening the details. By applying these filters over an image, we can exaggerate every tiny part of details in an image. Every tiny part of an image can give you more information if you're applying high pass filter. Okay. Thank you, students.